It's a pleasure to welcome Derek Schuff and Kai Ninomiya from Google. We know them very well. They're a very active contributor to the community. So we can't wait to hear from you guys. Take it over.
All right, great. Well, thanks for the invitation. My name is Derek Schuff. I work on WebAssembly toolchains and the WebAssembly specification. I'm a part of the Chrome team at Google. I'll let Kai introduce himself a little further down, but we're here to talk about WebAssembly and high-performance graphics. So the first question, obviously, what is WebAssembly? Most of you, I expect, have heard of it. A lot of people have heard of it, but it means different things to different people. According to our website, WebAssembly is a binary instruction format for a stack-based virtual machine, which is designed as a portable compilation target for programming language, enabling deployment on the web for client and server applications. So, that's a lot to unpack. The first thing to know, right, it's a virtual machine. I'm assuming most of you are familiar with other virtual machines, things like the .NET and JVM. And as such, it implements computation in software as a layer over whatever hardware you happen to be running on. So it's supposed to be portable across different hardware, and it's designed to be generated by a compiler rather than written by a human. But it's meant to allow targeting as many programming languages, hopefully all of them. And as the name implies, we work on deploying this for the web. But as the purple text implies, it's not just for the web, but we are also very much designing this to be embedded in other applications too, which I will talk more about further down. Unlike most other virtual machines that are in popular use, this one is a cross-company, cross-organization standard. We work with W3C, the WebAssembly Community Group and Working Group, to produce the design and the specification. That's where all of the action is in terms of determining what WebAssembly will be. And then among other design goals for WebAssembly are safety. Our specification includes a formal semantics with a type system that we have a soundness proof for. And between the type system and the various runtime constraints in the spec, we aim to ensure memory safety, although primarily this means memory safety for the embedder or for the user of the embedder rather than for the program. And there's also no undefined behavior, which is good for compile targets. So other goals include high performance. We try pretty hard to achieve that, subject to all of our other constraints that we have. So what's WebAssembly actually like? You could think of WebAssembly as a bit of a mashup between a traditional VM like the JVM and a machine architecture. It is a fairly low-level architecture. The instruction set and the primitive data types are fairly similar to existing machine architectures like ARM and x86. And that means that you can compile from C-like languages that only use primitive types and memory. This is one of the things that VMs like the JVM don't do as well, and it was a goal that we had for WebAssembly. And so you could think of it as being a sort of low-level virtual machine, but it is a bit of an odd mashup because newer versions of the WebAssembly that we've come out with in more recently do actually include what we call garbage collection support. The idea being that many embedders of WebAssembly, such as web engines, already have a great garbage collector that you would use with, for example, JavaScript. And the idea is allowing the guest languages to make use of the same garbage collector so they don't have to implement their own, and also so they can have better interaction with the host. And so this comes via the form of a type system with reference types, structs, and arrays, and that sort of thing. And we are continually expanding since we released the sort of minimum viable product around 2017. So we've added SIMD instructions, shared memory multi-threading, this GC feature, 64-bit memories coming very soon, various features for integration with JavaScript, things like stack switching and others, which are either recently released or in the pipeline. So there's plenty of use of WebAssembly already on the web. Most of the most common uses that we have for WebAssembly come from the more mature tool chains. Most of these target languages like C and C++ and Rust, which are what we call linear memory languages as opposed to GC languages. Um, not all of them, though. Yeah, you can notice C# in that list. Most of the well-known web uses are using the Emscripten compiler for C++. And so some of these include, ports of, in some cases, like 30-year-old legacy desktop code bases, things like AutoCAD and Photoshop. And then some of these are built as web apps from the ground up, things like Figma and Meet, Google Photos. So there's a lot of different kinds of code that people are bringing to the web with WebAssembly. Many of these also use WebGL, WebGPU, and of course, various other technologies that are already built into the browser. Zoom and Meet use it for video processing and audio processing. Most of these apps, even the ones that came from legacy desktop code bases, have written the UI for their app in HTML and CSS, which is a convenient way to write UIs, and then they may have something like a content area. Think like the image that you might be working on in an app like Photoshop, and these are rendered with Canvas or WebGL. Another kind of use case is more like a game type of use case, where you might just render all of your UI in WebGL. So like Unity games do this, for example. Once you start getting outside Emscripten, many of these apps use sort of frameworks that are more than just the compiler. So Microsoft has a framework called Blazor, which uses C# to develop apps that can be run on the client or on the server. There is Unity, which uses a mix of C# and C++ for games and similar applications. Pyodide is a port of Python to the web that you can go and, they have REPLs and various ways to bring, data analytics and things that are popular in Python. Because of course, you need more than just a compiler to make a language, to make an app, right? So a lot of these have other things that are packaged together with the implementation. There's also, aside from these more mature use cases, a lot of other newer things coming. Most of the sort of what I'm calling emerging implementations are targeting GC languages because the GC spec is fairly new and it opens up a lot of new possibilities for languages like Java, Dart, and Kotlin to run on the web. Frameworks play a pretty big part here too, again, because it takes more than just a language to make an app. Some of these, like Flutter, for example, are cross-platform frameworks that will let you build an app that runs identically the same on iOS and Android and the web and Windows and Mac. And a lot of developers really value that. Compose multi-platform is a similar thing for Kotlin. And many of these early adopting compilers are replacing, they already had versions of their framework or compiler where they were compiling to JavaScript, and now they're replacing those with WebAssembly compilers and getting some good results. I've got some links in here in the slide to recent talks that we gave about different ways that Google is using WebAssembly on the web, and some results that they've had from that. One sort of high profile result from that is usage with Google Sheets, which has its calculation engine, for the formulas. It's written in Java and it runs on both the server and on the client. And they're compiling that to WebAssembly, and they got a good speed up from doing that compared to JavaScript. So there's more detail on a bunch of that in these links here. Many of these applications also use WebGL, WebGPU, other graphics, even 2D Canvas, different ways to do graphics on the web. Of course, games are going to use this for rendering everything. Frameworks like Flutter and CanvasKit, they even use it for text rendering, which you can do instead of rendering with HTML in the DOM, and they do that so they can get pixel perfect accuracy across all of their platforms. And then there's a bunch of other frameworks for things like machine learning. It's very popular now. That's an interesting application because you can do this both on the CPU or on the GPU. Obviously, WASM has SIMD instructions, which are suitable for this kind of thing. And there's a trade-off here, right? Because obviously, if you can have access to the GPU, you get much higher throughput. But you have a higher startup latency. It's more complex, and so many of these machine learning frameworks support both CPU and GPU inference. And there are bindings available for these in Emscripten and other WASM tool chains, so you can use graphics along with your other WebAssembly code. But WASM is not just a web thing. WASM is a very general purpose way to express computation. And it is only computation. In particular, it doesn't include many of the things that you would expect from a platform or an OS, things like APIs, think POSIX or Win32. WASM is sort of strictly scoped to be to express the computation, but it is designed to be embedded into other platforms that will be the things that will provide these facilities to you. So, the first one is obviously JavaScript and the web, right? And so the W3C standards body produces specs for how WASM integrates with JavaScript, and these define things like how you're going to load and instantiate a WebAssembly module, how are you going to call into JavaScript and pass data back and forth between WASM and JavaScript, what web APIs are available. Obviously, there's lots of web APIs that are available to JavaScript, and how do you use those with WebAssembly. Although on the web, you typically don't use them directly from WebAssembly. You will be calling into JavaScript, but we try to make that as seamless as possible. For use cases which are not embedded into the web, you need another way to do some of this work. So there is a emerging spec called the component model, which tries to do some of the same kind of thing for non-web embeddings. So the component model defines language agnostic data types and interactions between basically it has this component abstraction which can encapsulate multiple WebAssembly modules and and express dependencies and things like that. It also has a way to declare and specify APIs, and which is another thing that you need if you're not on the web. And then another spec called WASI, the WebAssembly System Interface, is an effort to actually take the API declaration mechanisms that the component model provides and actually define a set of APIs. And of course, not every embedding is going to have every API, but for things that are common across different types of embeddings, the hope is that there can be common APIs as well. And there are already many different kinds of embeddings that are out there in the wild. So we have things like edge computing on a CDN done by Fastly. There's proxy configuration. There are several different kinds of blockchains, which are of course interested in encapsulating deterministic computations for smart contracts. Mozilla is using an in-app version of WebAssembly to sandbox untrusted browser implementation code. There are lots of cloud services trying to provide function as a service or serverless kinds of offering various different levels. And there's also another use case that's becoming more common where you actually embed WebAssembly into an existing app, which can be useful if you want to ship updates to your app or ship UI to your app without actually updating it. So my link in here is a blog post from Amazon describing how they do this for their Prime Video service, which is nice because if you're embedded into a TV that maybe never updates your app, you can keep refreshing your UI code without actually updating the app's native code. So I hear that you all are very interested in performance of WebAssembly. And I have some bad news, which is that there's no one answer for is WebAssembly fast. It depends on a lot of things, especially once you get beyond the web. And it depends on things like what are you starting with? What kind of code do you need to bring? Is it greenfield code that you are going to start writing now? Or do you have a large 30-year-old existing code base? Does it have a bunch of library dependencies that you will need to port? Do you have a whole bunch of like handwritten SIMD code that you maybe already have written with Intel intrinsics? By the way, if you do have that, Emscripten has your back. We will compile Intel SIMD intrinsics to WebAssembly, which is great, but it does come at a bit of a performance cost. You don't get quite the same level of speed up as you got on, if you were writing on Intel hardware. But it's a great head start. And of course, what are you comparing it to, right? What are the alternatives, right? Could you just write the app in JavaScript, or could you compile your app to JavaScript, as is common? on the web? Or are you going to come from the JVM or some other bytecode? Is that what you're comparing it to? Or are you comparing it to using containers or some kind of virtualization technology? It also depends on how you're going to execute this WebAssembly code once you've got it, right? Are you using a web engine or maybe Node.js? Are you running it in the cloud? Or do you have a tiny embedded device? What kind of engine are you doing? Is it allowed to JIT, or can you compile can you compile your code ahead of time? Or are you running on iOS where you maybe can't do any of those things and maybe you need to run an interpreter? And of course, what do you mean when you say performance, right? Are you talking about throughput, startup time, binary size? So there are many, many tools already that you can think of as building blocks for building your own embedding. And they have lots of different variants of how they compile, and they're optimized for different things. So the constraints of the use case that you're trying to build is what will determine what you can use and what your performance is going to be like. Yeah, so I just gave you, 2 whole slides of material about why any performance results that I give you might not be relevant, but all right, fine. Here's a benchmark for you. I know you're very interested in WebAssembly 64, so I compiled our compiler, our WebAssembly optimizer, to a native Linux application on my desktop. I compiled it to WebAssembly with Emscripten using a 32-bit and 64-bit WASM, and just tried it out on a test case. You can see that going from native to WebAssembly just by itself costs about 6.5% of performance overhead, and then going from 32-bit to 64-bit will cost another 23 or so percent. And the reason for the cost going to WASM 64 is primarily because this is Node.js, this is V8 that we're talking about. V8 uses several virtual memory tricks on WASM 32 to implement the memory safety, in particular the bounds checks for the linear memory, which are basically free on WASM 32. And currently they are not free on WASM 64. There's some overhead that comes with every memory access. The exact nature of this, again, is going to depend on your application. And in particular, there are probably some compiler-based analysis that we could use to sort of eliminate or coalesce bounds checks, which we have not done yet in V8. It's still fairly early days for WebAssembly 64, but this is sort of an upper bound on the cost from going from free bounds checks to not free bounds checks. So yeah, you may have questions. We can talk more about that after the presentation if you're interested. But for now, I will hand it over to Kai to give you more about WebGL and WebGPU.
Thanks, Derek. Hey all. Good to see some familiar faces here. So hey, I'm Kai Ninomiya. I'm a software engineer at Google working on WebGPU and WebGL. I'm also one of the specification editors of the WebGPU API spec. And I've been working on WebGPU ever since the very beginning, back in 2016. Next slide, please. So first, just an intro, right? So Derek already mentioned WebGL and WebGPU are quite popularly used in WebAssembly applications. These are two APIs that exist on the web for low-level graphics, and they have some really key properties. So one is that they're safe, right? Browsers can run your code without having to trust it, and this is the most important property of the web, and of course applies to WebAssembly as well. In addition, it's also portable, as just like WebAssembly. Your code can run everywhere with relatively little porting pain. It's very difficult to make GPU code quite as portable as WebAssembly, but we try pretty hard. And of course, WebGL and WebGPU are not just for the web. So WebGL has a native equivalent in OpenGL-ES. They're very similar to each other. And then WebGPU has a native equivalent in WebGPU.h, which I'll talk about some more later. Next slide. So WebGPU, if you're not familiar, is a successor to WebGL for GPU acceleration. It's standardized at the W3C as well. It has a new shading language called WebGPU Shading Language WGSL or WGSL. I will note, just put a note here that WebGL is not dead. We are still maintaining it. You can still use it for the foreseeable future. This is important for a lot of reasons. But anyway, WebGPU is built on the sort of modern style APIs that started showing up around 2014 to 2016, Metal, Direct3D 12, and Vulkan. And we are also working on a compat mode, which is targeted at OpenGL ES 3.1 systems, which gains quite a few devices, especially on Android and some of like Chrome OS and systems like that. It has a modern style. It's a very similar abstraction level to Metal, if you're familiar with it. There's no manual synchronization, no memory management, no unsafe knobs, of course. So it's still a little bit, gives you a little bit less control than Metal, but the sort of API style is similar. And of course, it has a modern feature set, including compute shaders, indirect calls, render passes, render command bundles, float 16, and a number of other features that we're sort of working on or have recently started rolling out. Next slide. So WebGPU has shipped in Chrome on Mac, Windows, and Android 12. It shipped close to a year ago, I think, on desktop. There are pre-release previews available in other browsers. Firefox Nightly and Safari Technology Preview both have options to turn it on, as well as Chrome on Linux and older Android devices, which especially Chrome on Linux support is a bit spotty because we have issues on certain devices. We have many early adopters of WebGPU, including Unity, who we've been working with for quite a while. They announced their early access WebGPU support in September of last year. Babylon.js and Through.js, we've been working with both of them from very early on in WebGPU to get their engines ported. And there are lots of other engines that have announced WebGPU support more recently as well, Pixie.js, PlayCanvas, and a ton of others. Next slide. WebGPU is out there, at least in Chrome, but there is lots more to come. There's lots more work to do. So one thing that is conspicuously missing is WebXR integration. Like I mentioned, WebGPU compat for wider hardware support. I will note that even with compat, the hardware support won't be quite as wide as WebGL. WebGL 1 and WebGL 2 go back a bit farther because they don't require compute shaders and certain features. Of course, there's Firefox and Safari support coming, and Safari support also means iOS support. And then Chrome on Linux and older Android will come as well at some point. Other things we're looking at, better WASM integration, especially for memory mapping and object management. We are eventually going to add multi-threading to the JavaScript API. It's quite complicated. And we have many other things that we're working on. And then also multi-threading in the WASM API, which there will probably be ways to emulate before even the JavaScript API ships multi-threading. And then there's lots of API and WGSL features in the works for advanced compute and graphics and machine learning and all these things. Next slide. So you may see a theme here. WebGPU is cross-platform. It's not just a web API. There are bindings to Rust, C, C++, and others. These are used on native and as well as WebAssembly. So in native, there are a few implementations. There's Dawn, which is the C++ library that Chromium uses. There's WGPU, which is a Rust library, which is very popular as a graphics abstraction library in the Rust ecosystem, and WGPU native, which binds that API to C. There's also WebAssembly bindings over the JavaScript API. So Emscripten and WGPU both both implement targets that you can use WebGPU in WebAssembly. And of course, JavaScript and WebAssembly outside the web. So Dawn has a plugin for Node that implements WebGPU, the JavaScript API that can again be used through Emscripten. And Deno implements, I don't know exactly what the implementation status of this is, but Deno implements WebGPU using WGPU as well. And I'll note that All of these cross-platform targets, the WebGPU API itself is still safe and portable. It's the same API. There are toggles, there are like knobs to turn off some of the bounds checking and things like that if you want to squeeze out more performance on native. But by default, it is essentially the same API that you're going to get on web. And if you use the core set of features, then you should be getting the same level of portability. Of course, there's caveats where the binding language is unsafe, like C passes an invalid pointer, but the API has the same level of safety in general. Next slide. So WebGPU.h is the C API that I mentioned. This underpins the language bindings for C++ and Dawn, the Go WebGPU project, and a bunch of others that are mostly developed by third parties. This is also a standardization effort. It's sort of unofficial, but we're standardizing it between the Dawn and Emscripten team and the WGPU maintainers. This is currently usable and is used by a bunch of applications out there, but the stability and interoperability are still in the works. So you can start building on top of this. You'll have to tweak a few things later on as we stabilize, but in exchange, you'll get access to more interoperable implementations. So right now it is implemented in Emscripten, which provides both the C API and Dawn's C++ bindings. It is mostly interoperable with Dawn. There's a few small gaps, but it's very close right now. And Emscripten and Dawn are both moving forward toward the eventual stable API that we will share with WGPU native. There are also some alternate C bindings called WASM WebGPU. Unity uses these. They are optimized for WebAssembly specifically rather than cross-compilation because Unity is not as interested in using WebAssembly outside of the web because, of course, they have native targets for all of the other graphics APIs. Next slide. So I'll talk about some performance stuff. GPU work is, of course, totally independent of the CPU and WASM once you get it there, once you get it to the GPU. But the API is really where you're doing all of the work, and graphics APIs are quite chatty. They do many calls per second or per frame, and this is still true in WebGPU, although there are ways to avoid it, including the render command bundles that I mentioned earlier, which let you pre-record and replay commands and avoid a lot of that overhead. But in any case, each call needs to get all the way from WASM to the GPU driver. And this means going in a browser, this means going out to JavaScript and then to the browser engine, and then across the process boundary to the GPU process of the browser, and then into the WebGPU implementation like Dawn, and then a driver. This is pretty fast, but every step is pretty performance sensitive. There's bindings overhead, especially in the JavaScript to browser engine step. There's serialization time and flush latency in the IPC step. And so there's lots of parts here that need to be optimized, but overall it performs pretty well. Next slide. So the Chrome team is, we are investigating ways to optimize WebGPU in both JavaScript and WebAssembly. So a couple of things that we're looking at, like these are all just previews of interesting things that we're looking at. One is reducing the overhead of bindings to V8. So that's the call from JavaScript or from the virtual machine in general into the web engine. So V8 into Blink. This is actually something we worked on a couple of years ago for WebGL, basically simplifying the calling convention from V8 into native code so that we didn't call out and then the native code had to call back into the virtual machine to get all the arguments and unpack all the stuff that we passed over. So that's something that we did a couple of years ago and got some great performance benefits, but we're also still working on like improvements to that optimization. Removing the JS trampoline seems like an obvious step, like trying to avoid going through JavaScript between WebAssembly and Blink. So we are experimenting with using WebAssembly's extern ref to bind the platform function from Blink directly into WASM. So we set it all up in JavaScript, but then we don't actually have to execute through JavaScript on the way out to Blink. And this is something that we are working on and have some promising improvements there. There's also lots of other things that like lots of other problems that we know about. So there's some indirections and lookups. There's multiple levels of integer handles going on when you're going from WebAssembly to use WebGPU, as well as WebGL. And we would like to avoid some of those indirections, but they're quite tricky to remove. And of course, we want to make this all, for WebGPU, we want to make this all work for multi-threading. And right now, each thread needs a way to look up JavaScript from the WASM JavaScript objects from the WASM handles, which has to be done on every call. And so we're looking for ways not only to reduce the overhead there, but also make this stuff all work for multi-threaded applications. Yeah, next slide. That's it for my section. Here's a bunch of links. If you have the slide link, you can go here and check these out. This is just a selection of resources that I picked, but these are some of the things that I mentioned, as well as a bunch of useful learning resources. So I recommend checking them out if you want to see what WebGPU looks like or get some hands-on experience with it. And that's it for me.
Wow. Thank you, guys. Thank you, Derek. Thank you, Kai. That was deep and extensive. Thank you very much. For that, we'll open up for questions. I may kick it off with one question. And forgive me if it's high level, but very naturally, I think what you guys said is some of the performance limitation also comes from the overhead of running in current generation browsers and the necessity to support things like that we call legacy, like JavaScript or whatever. If you wanted, we're a bunch of 3D guys here, and if you wanted to create a dedicated browser for 3D world that do not need to have the overhead of HTML and things from the past, I would say, do you think could you create a new browser architecture that would really deliver the performance? In other words, is the performance overhead really because of the legacy of the current browsers, or maybe another question is, if you were to write a new browser, how would you write it, knowing that you don't want to carry the legacy of the past?
Well, I would not describe what you're describing as a browser if it doesn't support HTML,
Okay.
or at least not a web browser, right? I mean, I guess what you're saying is, what if I wanted to make like a rendering engine for just like basically what you're talking about is reducing the set of APIs or functionalities that you're going to have, right? So you're going to say, maybe I just want WebGPU and like a canvas or something like that, right?
Yeah. And I want it all in
and
3D.
Right. In terms of overheads, I would say, at least from the WebAssembly perspective, there is some amount of overhead that you pay from just like, for example, if you're going to use V8 as your engine, if V8 didn't also have to have JavaScript, it might use different calling conventions. It might, there's a few things that it might do differently. But obviously, V8 has the advantage of being a very powerful JIT and has the optimizations that also apply to WebAssembly. So you could gain a little bit by doing that. In terms of raw computation, I don't know if it would be a lot. I mean, as you see from raw computation, we're fairly close to native, at least if you ignore something like platform-specific things like SIMD, right? So the other part of your answer is like, how much portability is your goal, right?
Yeah, we would want portability. I mean, we would like to create something that by definition allows portability.
Yeah, I would say most of the performance caveats that come with WebAssembly and running anything on the web really, for the most part, come from the fundamental properties that we can't get rid of, the security and portability. Security, of course, like memory safety. Portability is, something that that definitely advances over time, right? The set of features available across systems advances over time. We figure out ways to abstract things like SIMD and GPU features and so forth, so that you have access to them on more systems. Older hardware ages out of the market, and so you become able to use higher levels of functionality by default. So there is some fundamental lag there where there's features that you'll be able to use eventually, hopefully, but that aren't necessarily going to make it into the platform. Like they aren't going to make it into the platform nearly as quickly as they could make it into native, and that is just a requirement of portability. And so I think that like most of the stuff in the browser doesn't get in the way of performance for either WebAssembly or WebGPU or WebGL. They are pretty well siloed off into areas where we have a lot of ability to optimize.
Thank you. So let's open it up for questions.
Yeah, I had a question on Memory 64. You mentioned it's coming soon. Can you elaborate somewhat on that, at least from the Chrome perspective?
Yeah, I expect that we will get the standard ratified within a couple of months. Ideally, we have a in-person WebAssembly standards meeting coming up in June, and I'm expecting to be able to get it done by then. And then at which point, I think it's close to being shippable in Chrome, even if it's, I don't know how much, for example, bounce check optimization we might do in the future, but I think it's more or less in a shippable state now. So yeah, I mean, I'm talking like a quarter, right? As in terms of when we can get it out the door, it's very close. And then there is an implementation in Firefox. I don't know how close to production ready it is, but I would imagine they'd be able to ship it before too long. And then, yeah, there's no point in speculating anything about Apple. They do stuff on their own time.
Yeah, so quick follow-up there. The overhead of the bounce checking and all that you show within the graph, like how much opportunity do you think there is for optimization there over time? Like,
yeah. So, and again, I'm talking specifically about what you could do on the web, which is maybe or maybe not what you could do if you were doing your own, if you're doing your own embedding, you might have different options, right? Depending on what kind of virtual memory facilities you can do and like what platforms you have to run on. Some of our limitations are because, virtual memory on Windows works differently than it does on Android, let's say, right? So I think there is some opportunity. I don't think it will ever go all the way back down to free, the way it is on Memory 32, but I think there will be, there's an opportunity to do some compiler techniques like hoisting bounce checks out of loops and coalescing them and things like that. So, I mean, hopefully we could, remove some, I don't want to pick a number like, let's say half, but like somewhere in this ballpark of like a significant percent, but not all of the remaining overhead can go away. But as long as you have the portability and some of the constraints that V8 has, I don't think it's ever going to be free.
yeah, thanks. That's very helpful.
Next question, Ben.
Hey, everybody. Hi, how are you? Great presentation, Derek and Kai. Much appreciated. Learned a lot. Kai, two things that you had to pass through very quickly that I'm particularly interested in, especially WebXR and the implementation of that. And there is nothing that the WebXR community is more excited about than WebGPU implementation. So I was wondering if first you could flesh out a little bit of what that sort of timeline and roadmap and things that need to be done, who's doing it, and second of all, you made a comment about Unity's commitment to their implementation of it, and I'm interested if you could drill into that a little bit.
Yeah, sure. So as far as WebXR, it's very hard for me to give a timeline on it. We have simply not been able to prioritize it. We have so many other things that are very important to do for WebGPU, including beefing up our test suite a lot before we have other implementations and need to make sure that they're all interoperable, as well as other like really important features that are like that were missing from the very first version, and compat, which is going to be important for a lot of reach to older devices. So WebXR just hasn't been something we've been able to prioritize. Brandon Jones is on our team. Brandon Jones, who works on WebXR, is on the WebGPU team. We have the expertise and folks to do it, but also like Brandon spent a good while working on shipping on Android because Android is very important. So it's really hard for us to say. I would say that as far as standardization, that if there are people who want to go to the WebXR group and do the work of designing and sort of proving out WebXR integration for WebGPU, it would probably help things along a bit. Brandon did publish a proposal for how that integration would look a few years ago, but I don't believe that it has seen a whole lot of progress since then. And then as to the second question about Unity, yeah, so Unity, I don't of course know their like launch plans or anything, but Unity shipped the pre-released early access version last September, which is like not, you have to do some trick to get to turn it on. It's very easy, but it's like not available in the UI. You have to know about it and learn and like do something to turn it on. But they can target WebGPU. As of that release, it was not perfect. It did pretty well on most scenes using the universal rendering pipeline or whatever it's called. But they've ironed out a lot of bugs since then, and so things are pretty reliable now. The high definition rendering pipeline is something that we're very interested in seeing, but I believe they're not quite there yet, and I think it will be some time before we're able to ship the few missing features that they need in order to implement that. But I don't know 100% for sure. But I do know that they are. I mean, there was a news article literally yesterday where the interim CEO of Unity was saying WebGPU is important to us. So I think that can give you some confidence that they are investing in it, continuing to invest in it.
Thank you. That was really helpful. On your suggestion that, like people who could step up in terms of making that ask and saying to the community, hey, like, what could I say? Because like I can reach out to the WebXR community, but I need to target the right people with the right language to be able to do that. But I think that the more sort of, fire that we could put under that to get the right people involved would help everybody to see it through quicker. I spoke to Ken Russell about a month ago, and he's sort of identified a similar sort of prioritization going on.
Yeah. Well, he's my boss, so hopefully we say the same things. But yeah, I would say that one thing that makes it difficult to get WebXR done is that we are the only browser that's shipping WebGPU yet, right? And so the other browsers are certainly going to be prioritizing shipping WebGPU before trying to figure out how WebXR is going to work for WebGPU. And that may slow things down a bit in terms of getting it standardized. The other thing is an implementation. Of course, like we would love to work on an implementation in Chromium, but we haven't had the time to do so. However, I think would probably be willing to accept contributions actually working on the implementation, like of a proposal and proving it out and making sure it works before we go and standardize the thing. Like before we ratify the thing. So I would say like reach out to Brandon Jones if somebody wants to work on an implementation in Chromium, like we can help a bit. We won't have tons of time to dedicate to the project, but we're always happy to help things done.
Well, thank you. That was great info, and I applaud what you guys are doing, and so good luck. I look forward to seeing that seen through as soon as possible, especially with the WASM integrations and all the good that's going to come from that. Because really, the thing that's holding WebXR back is performance. Thanks.
Thank you, Ben. And I would not say that web games were a theme at GDC, but they were certainly more mentioned than ever about that, and people being very eager to see there is a way there to solve their games distribution problem. So, Michael Cass, you're next.
Yeah, so if somebody wants to make a custom application that uses WebAssembly and WebGPU to execute unsafe code, what's the right way to do that? Is it to use V8? Is it Chrome Embedded Framework? Do they support both things together and making them play nicely? And also, if you want to use WASM 64, what's the path for that?
Yeah. So before I answer that, let me add one caveat to the answer I gave about WASM 64 a minute ago, which is that CPU vendors do keep adding interesting things to their hardware, including like instructions for memory safety. And so it's possible in the medium to long term that we'll get CPU instructions that can help us cut or eliminate the cost of like bounds checks on some platforms. So, maybe I said never too soon, but I'm actually hopeful that could happen in the long term. So, okay, so the question of like, yeah, if I want to build an embedding, which engine do I want to use? Like that is a surprisingly complicated question that the answer to which will depend a lot on like what kind of platform do you want to run your implementation on, right? And how much do you need to reuse, right? So for V8, like so you can certainly embed V8 into many other kinds of applications that are not web. Like there are lots of people doing this. Node is an obvious one, but there are others where it's embedded into things like database engines, or if you look at what Bloomberg has done, like the Bloomberg terminal embeds most, like it's basically a version of Chromium plus like extra like C++ APIs that they've added on top. So like that's not quite like the Chromium embedded framework, but it is in the same flavor. So it can definitely be done. And of course, that will give you the entire web platform. It'll give you, JavaScript. Some people say, I want my thing to be as small as possible, so therefore I don't want JavaScript. And in that case, V8 might not be a good choice for you because right now there's not a good way to separate JavaScript from WASM in V8. There are other engines, the most well-known of which is WASM Time, which is basically like a framework that uses a couple of different compilers to compile WebAssembly to native, but it's like a WASM-only engine. And if you go that route, then you will need to essentially define your whole set of APIs that you want to expose to your untrusted code, right? And that is basically what the component model and WASI are for. And this is what most of the non-web embeddings of WASM are doing. And so you will pick a set of APIs. There is a WASI, if I remember correctly, there is a WASI proposed API that is meant for exposing the GPU, right? So, like I would imagine you might just take a GPU API and then implement it on top of Dawn, for example. And then, then it comes down to like, what language do I want my implementation to be built in, and where do I need it to run, basically.
And what about Chrome Embedded? Does that get you everything?
That it should. So I'm trying to remember exactly which layer of abstraction Chromium embed. So there is a thing called the Chromium embedded framework, but it's also true that Chromium has a layer that we call the content layer, and this is the layer that like other browsers on Chromium use, so like Edge and Opera and those. And there is like an abstraction that tries to separate the parts that are common to the web platform, which the parts that are like Google Chrome specific. And so that's another possible way you could slice the Chromium code if you wanted to bring the whole web platform with you.
Thanks.
I don't know if that quite answered the question, but yeah.
All right, it's good. Neil, I'm going to come to you in a second. I'm going to stop the recording now. We're at time.